To measure the vast distances between stars and galaxies, astronomers use a unit called a light year. A light year is the distance that light travels in 1 year. This may sound like a measure of time, but it's actually a measure of distance, an incredibly large distance. To put it into perspective, imagine traveling at the speed of light. You could travel around the Earth 7.5 times in 1 second. Now, imagine traveling at that speed for an entire year. That's the distance covered by a light year. Our closest star, Proxima Centauri, is about 4.24 light-years away. This means that the light we see from Proxima Centauri today actually left the star 4.24 years ago. We're seeing it as it was in the past. The farther away an object is in space, the farther back in time we are looking. While light-years are a convenient unit for understanding cosmic distances, astronomers often prefer to use a different unit called a parsec. A parsec is a unit of distance equal to about 3.26 light-years. The term parsec stands for parallax of 1 arcsecond. It is based on a phenomenon called parallax, which astronomers use to measure distances to nearby stars. 1 parsec is the distance to a star that exhibits a parallax angle of 1 arcsecond. An arcsecond is a very small angle, equal to 1/3600th of a degree. Parsecs are particularly useful for measuring distances to stars within our own galaxy and to nearby galaxies. Astronomers use sophisticated telescopes and instruments to measure the tiny parallax angles of stars. From these measurements, they can calculate the distances to those stars in parsecs. Imagine looking at a nearby object with one eye closed, then switching eyes. You'll notice that the object appears to shift slightly against the background. This is called parallax. Astronomers use the same principle to measure distances to nearby stars. As the Earth orbits the Sun, our viewpoint of nearby stars changes slightly. This change in viewpoint causes the stars to appear to shift slightly against the background of more distant stars. By carefully measuring this apparent shift, called the parallax angle, astronomers can calculate the distance to the star. This method is most accurate for stars that are relatively close to Earth, within a few hundred light-years. For more distant stars, the parallax angle becomes too small to measure accurately. To measure distances to objects that are too far away for parallax measurements, astronomers rely on standard candles. These are objects with known luminosities, or intrinsic brightnesses. One type of standard candle is a Cepheid variable star. These stars pulsate in a predictable way, and their pulsation period is directly related to their luminosity. By measuring the pulsation period of a Cepheid variable, astronomers can determine its luminosity and calculate its distance. Another type of standard candle is a type Ia supernova. These are incredibly bright explosions that occur when a white dwarf star explodes. Because type Ia supernovae have a very consistent luminosity, astronomers can use them to measure distances to galaxies billions of light-years away. In the early 20th century, astronomer Harlow Shapley made groundbreaking discoveries about the size and shape of our galaxy using Cepheid variable stars. At the time, astronomers still debated whether the Milky Way contained the entire universe or whether other galaxies existed beyond its boundaries. Shapley used the period luminosity relationship of Cepheid variables to measure the distances to globular clusters, dense groups of stars that orbit the Milky Way's core. He found that globular clusters were distributed in a spherical halo around the Milky Way, not centered on the Sun as previously thought. This discovery demonstrated that the Sun was not located at the center of the galaxy, as was commonly believed at the time. Shapley's work revolutionized our understanding of the Milky Way and our place within it. Today, astronomers use a variety of advanced techniques to measure cosmic distances and map the universe. Radio telescopes, for example, can detect radio waves emitted by objects in space, even those obscured by interstellar dust. By studying radio waves from pulsars, rapidly rotating neutron stars, astronomers can map the distribution of matter in our galaxy. Radio observations have also been crucial in studying the rotation of galaxies. By measuring the Doppler shift of radio waves from different parts of a galaxy, astronomers can determine how fast the galaxy is rotating. This information provides insights into the distribution of mass within the galaxy, including the presence of dark matter. One of the most surprising discoveries in modern astronomy is the existence of dark matter, a mysterious substance that makes up about 85% of the matter in the universe. Dark matter does not interact with light, hence its name, but its gravitational influence can be detected on the motion of stars and galaxies. Astronomers first inferred the existence of dark matter by studying the rotation curves of galaxies. They found that stars in the outer regions of galaxies were moving much faster than expected based on the visible matter alone. This observation suggested that there must be some unseen mass, dark matter, providing the extra gravity to hold these stars in their orbits. As we continue to explore the universe and develop new technologies, our understanding of cosmic distances and the vastness of space continues to evolve. We've come a long way from the days when people believed that the Earth was the center of the universe. Today, we know that our planet is just a tiny speck in a vast and awe-inspiring cosmos. The light from distant galaxies takes billions of years to reach us, offering a glimpse into the universe's distant past. The vastness of space also means that the timescales involved in space travel are immense. Even traveling at the speed of light, it would take thousands of years to reach even the nearest stars. But this doesn't mean that interstellar travel is impossible. It just means that we need to keep exploring new technologies and pushing the boundaries of what's possible if we ever hope to venture beyond our own solar system. Join us if you liked this information as we explore the cosmos together.